Welcome to the Chapter 3.4 lesson video. We're going to be talking about factoring polynomials. Now, some of this will be stuff that you already know and are familiar with. Some of it's going to add a little bit to old methods, and some is going to be brand new. So let's go ahead and get started. So first things first, we're going to talk about the greatest common factor. This is something you should check every time you go to factor a polynomial. You should always check for the greatest common factor first. So you're going to look through and the coefficients and say, all right, those are all divisible by 2. And you'll also look through and see if they all have common variables. They all have an x. So our greatest common factor here is 2x. We can pull that greatest common factor out. So we divide each term by that 2x, leaving us with an x plus 3y and a minus 6. Once we pull the greatest common factor out, then if possible, you can continue factoring the inside. In this case, you can't. If you can, you keep factoring. If not, you go ahead and box your answer. Do not forget to include your greatest common factor in your final answer. All right, so our first method here is a new method, a brand new method. There's actually two of them here. We have what's called the sum and difference of cubes. Now, the sum and difference of cubes happens when we have two things that are cubes, values being cubed, separated either by an addition or by a subtraction sign. So this is sum of cubes, this is difference of cubes. They both have kind of a similar form, but things get written a little bit differently. So, in sum of cubes, the way we write it, the way we factor it, is it's going to be a binomial, which is the bases of the two cubes added together. Whatever sign is up here is going to match this sign right here. And then the second thing that factors is a trinomial, and that trinomial is that a value squared minus, the sign is always going to be opposite of what's up there, minus the two bases being multiplied together, plus the second base, this b value, squared. All right, so that's the sum of cubes pattern. The difference of cubes pattern is very similar, but there's some key differences. So our difference of cubes pattern looks like this. The first parentheses is a minus b, so this sign matches what's up here. And then the second parentheses is that a value squared plus a times b plus b squared. All right, so let's look at these two factoring methods real quick. What you're going to do is you're going to either make it a sum or difference of two things being cubed. You might need to rewrite some stuff. We'll see some examples of that in a second. Then what you're going to do is you're going to look at these two bases. Your first binomial is going to be just essentially what you have here, but without that cubes part. So it's just going to be a plus b or a minus b. The second parentheses is going to be that first base a squared, and then an opposite sign times the two bases, a and b, and then plus the second base, b squared. Over here in difference of cubes, it was that first base squared and then an opposite sign of our binomial plus the two bases, a times b, and then the third term is always plus the second base, the b squared. So we're going to go ahead and we're going to try this on the next slide. I really think it's essential that everyone makes sure they get these written down somewhere where they can look at them and reference them until they have them memorized. But this is a new form of factoring. This is called sum and difference of cubes. We're going to practice it twice on the next screen. All right, so on this next screen, we have x to the third plus 27. Now, what we're going to do is we're going to rewrite this as a sum of cubes. Right now, we have x to the third, that's already written as something cubed, plus, that's a sum part. 27 is something cubed. Now, if you don't know your cubes, you should probably learn your cubes up a little ways. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. That's probably a good start, but you should know your different values cubed. So I just said it over there. 27 is 3 cubed. So we have our two bases, x and 3, and they are being cubed. So this is a sum of cubes. So our pattern here should be the first base, x, plus the second base, 3. That's our binomial. Remember, the sign matches in the binomial. And then our second factor is a parentheses. It's the first thing, x squared. An opposite sign, the opposite sign of plus is minus. And then we multiply the two things together. So we're going to multiply the x and the 3 to make 3x. And then the last one is always positive, and it's the other base. In this case, that's the 3 squared, which is 9. So there we go. We have now factored. This is our final factored answer, x plus 3 times x squared minus 3x plus 9. All right, we're going to do this again on this next one, but we got to rewrite it as two things cubed. This time it's going to be a difference of cubes. We can tell by the subtraction. So this first part right here, it is a 8x cubed. So we're going to rewrite that. 8 is 2 cubed. So we're going to rewrite this as parentheses 2x parentheses cubed minus y cubed. So our first base is 2x. Our second base is y. So we'll go ahead and we'll write our two parentheses. Our first parentheses is the same bases, 2x, same sign, minus y, our second base. Our second parentheses, we're going to take that first value, 2x, and we're going to square it. 2x times 2x is 4x squared. We now need the opposite sign of what's right here. So we're going to write a plus sign, plus. Now we're going to multiply the two bases together. 2x times y is 2xy. 2xy. And then lastly, we're going to take our second base right here, y, and we're going to square it. So that's plus, this one's always positive, y squared. So that third term in the trinomial is always positive, regardless of sum or difference of squares. All right, we're going to practice this some more in class. This one takes a little bit of practice, but basically what you're going to do is you're going to either rewrite your thing as a sum of cubes or a difference of cubes, and you can usually tell that it's a sum or difference because it kind of looks like that difference of squares, but those numbers are not squares. You're going to rewrite it as a sum or difference of cubes, as something cubed plus something cubed or something cubed minus something cubed. And then really, once you memorize this pattern, it gets a lot easier. It's the first base minus the second base if it's a minus, and then you square the bases on the outside, and then it's an opposite sign for that middle term there. All right, let's go ahead, let's keep going. All right, our second to last thing for this video is factoring polynomials that are in a quadratic form. Now, this is kind of an expansion on something we already know how to do. We already know how to factor quadratics that are in a x squared form. Now, if a polynomial follows that pattern in some way, then we can factor them kind of like we would normally. So this says polynomials can be factored using our normal methods as long as we rewrite them in the form something squared plus b times, or au squared plus bu plus c. Basically, as long as the degree of our first term is double the degree of our second term, we can factor it with just like a normal diamond problem, right? So as long as the degree of the first term is double the degree of the second term, we can do this like a normal diamond problem. So here's what we would do here. We would say, all right, let's look. The degree of the first term is 6. The degree of the second term is 3. Well, that means we can factor like normal. So we'll go ahead and we'll do our normal diamond problem. What multiplies to 10 and adds to 7 is 2 and 5. Now, we don't write our answer like normal, though. Rather than writing x plus 2 times x plus 5, we need our first terms to multiply to make x to the 6. So what we're going to do is we're going to make that x to the third plus 2 and x to the third plus 5. So really, your first term is whatever this middle term is. It's going to be half of the degree of the first term. So you're left with this x to the third plus 2, x to the third plus 5, x to the third times x to the third. That does make that x to the 6. 5x to the thirds, 2x to the thirds, that makes our 7x to the thirds, and 2 times 5 makes 10. All right, so there we go. We have our factoring. It was very similar. The only difference is our degrees are a little bit higher. Let's go ahead and practice this. All right, so we have 2 here. Let's double check the first one. The degree of our first term is 50. The second term is 25. So the degree of the first term is double the degree of the second term. Perfect. We can go ahead. We can do a diamond problem. We can say what multiplies to our c value, 6, and adds to our b value, 5. That's going to be 2 times 3. So we've factored, except now instead of just making it x plus 2x plus 3, we got to make it x to the 25th plus 2, and x to the 25th plus 3. All right, so since it started as a higher degree, it basically ends as a higher degree. Now our next one is a little tricky. 11 and 6. 6 times 2 is definitely not 11. However, if we look through 2x to the 11th, 2x to the 6th, 40x, there is a common factor hiding here. We can pull out a 2x from each term. That'll leave us with x to the 10th plus 2, not 2, plus x to the 5th minus 20, and that's our greatest common factor being pulled out. Now we can factor this inside piece using our methods because 10 is double 5. So now we'll go ahead and do our diamond problem. We'll say what multiplies to negative 20 and adds the positive 1. I think that'll be 5 times negative 4. So don't forget your common factor you pulled out earlier. So that common factor you pulled out earlier is 2x. And then this isn't x anymore. This is x to the 5th plus 5 times x to the 5th minus 4. And there's our final answer. So it's a lot like our normal diamond problems. You just have to be careful to make sure that you adjust for these higher degrees. So whatever it is if the first degree is double the second degree, then we can just factor like normal, except the degrees above our x's has to be whatever that second degree was. So same thing here, 10 was double 5, 10 was double 5. So when we factored it, we used x to the 5th, half of that x to the 10th. All right, our last thing for today is something called the factor theorem. So we talked about synthetic substitution last class, and the factor theorem says, hey, if you do synthetic substitution and you end up with a remainder of 0, then whatever you substituted in, the kind of opposite of it, so if you do 7, that means x minus 7. If you did negative 3, it'd be x plus 3. Whatever it is a factor of the polynomial. So if we want to see if x minus 7 is a factor of this polynomial, we'll do this synthetic division process. So to do that, to see if x minus 7 was a factor, we're going to plug in the 0 for 7. So what minus 7 is 0 is positive 7, so that's our top left box. We'll take the coefficients, that's 1, negative 5, and negative 14. We're going to drop down our first. It's a 1. 7 times 1 is 7. Negative 5 and 7 make 2. 7 times 2 is 14. And look at that, our remainder is 0. What that tells us is that x minus 7 is a factor of this polynomial. And not only that is that x minus 7 is a factor, what we have right here is the other factor. Because remember, we just decreased the degree by 1. It was an x squared. So that means our other factor is an x plus 2. Well, we should have kind of already known that, right? Because if I asked you to factor this polynomial right here, you should probably be able to say, all right, negative 14 and negative 5. My factors are going to be negative 7 and positive 2, right? Because negative 7 times 2 is negative 14, and negative 7 plus 2 is negative 5. So our factors would have been x minus 7 and x plus 2. That is how we can check if there's factors. So if there's ever a remainder of 0, then it means kind of the opposite of it is a factor, right? So we wanted to see if x minus 7 was a factor, so we did synthetic division with a positive 7 here. All right, let's go ahead. Let's try this here. It says, show that x minus 2 is a factor of this big long polynomial. And then after you're done, see if there's any more factoring you can do. So here's what we're going to do. We're going to set up our synthetic division. We're going to go ahead and do the opposite of minus 2 is positive 2. We'll list our coefficients. There's 1x to the third, 3x squareds, negative 6x's, and negative 8. We'll draw our line and put our bottom box for our potential remainder. We'll drop down the 1. 1 times 2 is 2. 3 plus 2 is 5. 2 times 5 is 10. 4. 2 times 4 is 8. 8 minus 8 is 0. We have a remainder of 0. Because we have that remainder of 0, it means that not 2, but x minus 2 is a factor. All right, so we now have a factor here. We have x minus 2 as a factor. Our other parentheses is made up right here. Remember, degree is 1 less, so it's not x cubed, it's x squared plus 5x plus 4. Now you should remember it asks us to factor it completely, so we should double check and see if that second parentheses factors any further. Does anything multiply to 4 and add to 5? Yeah, 4 times 1. So our fully factored answer, f of x, equals that x minus 2 that we double checked times x plus 4 times x plus 1. All right, so now if we wanted to, we could do a polynomial graph with this. When we had this initial form up here, we didn't really know how to graph that, but now that we have it in this factored form, we can make our little squiggly line polynomial graph, and we'll talk about that in a future lesson video. All right, so just to refresh, if you want to check if something's a factor, you plug in its opposite or its 0. What would we plug in to make that equal 0? We plugged in 2. If the remainder is 0, then it means that it was a factor. And then our other factor, our other parentheses right here, which we can always then double check and see if it can factor using any other methods. This is another thing that will take some time to review in class. So if you have any questions, please reach out to me and I'll be glad to help you out. Otherwise, I'll see you in our next live session. And until then, I hope you have a great day.